All right, let's discuss the most general sequencing operation that we have in the world of I/O actions. And this operation is called bind, and it is written greater equals. It's an operator that is looking relatively similar to our basic sequencing operator, and even its type is relatively similar. It also takes two I/O actions, one of type IOA and one of type IOB, and combines them into a single I/O action, and the effects of these two actions will happen in sequence. But the big difference that makes an enormous difference in practice is that we do not just have to give the second action of type IOB, but the second action can use the result of the first action, which is of type A, as an input. So as the second action here, we actually provide a function, and to this function, we will get past the result of the first action, and we can use the result of the first action to decide what we want to do next. And that can be, depending on what we're getting, something mildly or even drastically different. Right? So it also means that even though the result type of the overall action is B again, we are now not necessarily discarding the result of the first action at all, because the second action can depend on the first, and therefore in particular can use A in all sorts of places, this argument of type A, including its result. So it can still decide to return this result of the first action as part of its result. All right, so let's look at this in practice. Right. Let's look at an example. So as a first example, let's discuss combining two functions or actions that we have been looking at a lot already, namely getLine, which is of type IOString, and putStringLine, which is of type string to IOUnit. And using these two, we can now write a single action that reads some input and prints back that input. Now that may not sound so spectacular, but we couldn't have been doing that before. Because in order to print back exactly what we've just received as an input, right, that means that the second action is influenced by the result of the first. And we didn't have that opportunity using just fmap or lift_a2. We would have had to decide in advance what we're going to print as the second action, what kind of string. We could not have made the input from the first action a part of that string, or let that influence the string we're going to print next. Right? So this is really, even though it's not particularly spectacular yet, it's something that we could not have done before. So let's just write it like this. It may be surprising that the types work out, but remember what the type of bind is. So it's IOA to A to IOB to IOB. And if we apply bind to getLine, we get that getLine is of type IOString, so A must be string. So if we have supplied the first argument to bind, we're now expecting a second argument of type string to IOB, right? And if we look at the type of putStringLine, it has string to IOUnit, so that just matches up here. So the B must be unit. So if we have applied both arguments, getLine and putStringLine, then we are just left with an IO action of type unit. And this application written with the bind and prefix form is of course exactly the same as the infix version up here. So that's why it works. It's perhaps a little bit more interesting if we actually do something else with the string. So we can do something like echo reverse. If we want to print back the string in reversed form. So how does that work? Well, very often it's useful to use bind with a lambda expression. So here we can basically just pick up the result of the action that we have written here. So this is the line that we have just read. And now we can call putString line of reverse of x. And now this whole lambda term here is still of type string to IO unit. So it can still act as the second argument of bind. And if I reload here and I try these actions out, so let's try out first echo. I type ABC, I get ABC back, printed back. And this is now part of the action, right? So it's not the result of the action. The result of the action is unit and is not shown at all. But as part of the IO action, the string is printed back. And if I do echo reverse and I type ABC as well, I get CBA back. Right? I could also do echo twice, where I type something in, right? Again using getLine. But now I want to print the same string back twice. Okay. How do I do that? Well, I can do putString line x. So that is basically exactly the same as what we're doing up here. But now I can use sequencing again, and I can use basic sequencing, for example, rather than bind. Sorry, not y, putString line x again, y is not in scope. And actually, the greater, did we redefine this? We redefined it, but it is available. So what's the problem? Oh, it's an ambiguous occurrence. I have not hidden it right now, because we have a redefinition of greater. Or actually, let's just get rid of our redefinition of greater and just use the built-in version. Good. And these parentheses here I would not actually even need. They were just for emphasis, because a lambda term usually expands as far to the right as possible. So it starts here, and all this is the second action. And even though the second action is again a compound action, that doesn't matter, right? We can sequence many things together. So echo twice. If I now type ABC, ABC, I get ABC printed back twice. Right? Or I can do a transformation of the string and a duplication. So I can do something like shouting back, right? Would be an option. So I can write a shout function, perhaps as a first or shout back twice. Let's just do it all in one go. Shout back twice. So the idea would be here that we read a line, and again we want to do something similar, but not with the same string. We want to modify the string, so we want to apply some transformation to it. So we can use a let expression here. So let y equals something to the string. So that could be reverse, but in this case we actually want to turn the string into uppercase letters. And I forgot the lambda here. So how do we turn a string into uppercase letters? Well, there is a function in the data.character module, which is called toUpper, which can turn a single character into its uppercase variant. So if we apply toUpper to lowercase x, we get the uppercase x. So if I just map toUpper over a string, I get the uppercase variant of the string. But toUpper, I have to import data.character. So I have to add that module import in the beginning of my module. And now shout back twice if I try it out and I type ABC, I get the uppercase string ABC printed back twice to me. Okay? Now, this is not necessarily easy to read if we structure it like this. So there is a nicer style of writing this, and actually it's a little bit of an unusual style, but it makes sense for I/O actions to basically take a form where we do something essentially like this, where we structure the bind in such a way that we keep the lambda part of the lambda term that's following on the same line, because then we basically match up the result of the I/O action get line, like the name that we're giving to the result, with the action, right? So they're close together because X becomes the result of the get line action. And then this X is available in the whole rest of the computation. Can use yet another example in a similar style where we read two lines and then perhaps do some operation on both of them. So combine lines, perhaps. So here we could read one line, and then we could read another line, and then we could do something with the two lines. So perhaps again put string line, but now we just basically print them together on one line with a comma in between. That would be one option. So we could use using list concatenation plus plus. So this type checks, and if we try it out and I do ABC and then DEF, I now get ABC comma blank DEF printed back. Right, so I get these two things combined. And again, you might think this is something that we should already have been able to do with lift A2, because aren't we just doing two things and then combining the result, right? Isn't program 1 almost the same? It's almost the same, but the decisive difference here is that here we've just been combining the results. We've not actually been printing things back, right? So we've been reading two lines and then concatenating the results. So that's the point to which we could get with lift A2. And we can still do that here. We can like write this differently using lift A2. That's just a different style. So if we use lift A2 of getLine, and then say, rather than concatenating these two things directly, I want to put a comma in between. Right? But at this point, we have an I/O action of type IO string, and there we haven't actually printed anything back yet. Right? And if we want to print that string back that we have been obtaining from the previous inputs, then there is no way but to use bind. So we would, if we want to like start with this lift A2 invocation and do the same thing, then we now have to pick up the combined result again. So let's call it C for combined, and then print that. So this is a different way of achieving the same thing. Again, if I type A, B, C, D, E, F, I get these lines combined. Right? So this is a different option to do the same thing. Now, it turns out that using bind, we are in a so general and powerful position that we can recover basically all the other operations that we have been writing before. So we had already seen that, for example, the basic sequencing operator is expressible in terms of lift A2, right? But basic sequencing is also very easily expressible in terms of bind. if we wanted to do this. So if we have one action, let's say IOA, IOB, and another action, we can just do IOA first, and then we can use bind. And now we get access to the result of the first action, but we can just choose to discard it. And then we can just do IOB. And that is a perfect definition of basic sequencing in terms of the more general bind. Now this will clash again or be ambiguous if I actually start using it, but it's a valid definition. Now, we can also ask ourselves now, can we re-implement fmap or lift-a2 themselves in terms of bind? And we almost can. There is just one other ingredient which we are still missing, which is a little bit absurd actually. So if we consider we would like to re-implement fmap on IO, like the fmap functionality, just in terms of bind. And so we want to write a function of this type. Now we get a function f and we get an IO action of type A. And remember what I said, what fmap is doing is creating a new IO action that has exactly the same effects as the first one, and then it just applies the function to the result. So that's the starting point we're taking here as well. We're going to start just by doing IOA, and then we use bind, and then we get access to the result, which is of type A. And then we would like to apply f to A, but this has the wrong type now. F applied to A, f goes from A to B, right? And f applied to A therefore is of type B, but we need something of type IOB. So the question is, can we turn something of type B into type IOB? And the answer is yes, that should be relatively easily possible. That makes total sense, because what this type IOB says is that it is an action that performs various effects, right? If executed on, like, with the outside world. If the plan is put into action, we interact with the outside world in potentially many different ways. So why should we exclude the option to not interact after all, right? If we can potentially do many different actions, why do we actually have to force to, like, perform at least one real side effect? And that doesn't make sense. So an IO action actually in practice has the option of performing arbitrarily many side effects and ultimately coming up with a result. And if we don't want to do that, then there is a function called return, and this function can turn something that is of type A into something that is of type IOA. So return can embed a result that we already have available and can embed it to be an IO action that, when executed, performs no actual effects and just delivers that result. And if we have return, then we can complete this definition and make it type correct as follows. And then it really captures this idea that I mentioned before, that fmap just, like, basically runs the original action and applies the function to the final result and does nothing else. Right? So return does not have any real side effects. It just lifts something into the world of IO actions. And then if we have return, we can actually implement lift-a2 as well in a very similar style. So we again have a function f, and we have two IO actions, IOA and IOB, and we simply start by doing IOA, and we, like, pick up the result, and then we do IOB, and we pick up the result, and then we have been putting IOA and IOB in sequence, and we have the two results available. And then we don't actually want to do any further effects, we just want to combine the results. So we can use return again and apply f to A and B. And f applied to a and b is giving us a c, and return applied to this is giving us an IOC. And this type checks. So return, that's a missing ingredient, and bind together, they're really the primitive operations that we need, together with like other sort of actually useful built-in I/O operations such as getLine that read a single line, but and or putString that prints something to the screen. But with these ingredients, we can basically do arbitrary programming, because we still have recursion, and recursion is very powerful, and we still have our expression language. We can do if then else and all sorts of other things and operations. And now we can write real programs that are involving I/O, complicated plans that involve loops and case distinctions and so on and so forth. There's hardly any limit. If you have a sequence of binds, right, such as here, it's perhaps enlightening once more to look at the scope, right? Because really we have one application of bind here, and the first argument of this is this IOA action, which is of type IOA. And then the second argument of this first occurrence of bind is the entire rest of the computation, the part that I have highlighted now, right? That goes from this lambda A up until the very end. And this whole function is of type A to IOC. I don't think I can get... oh yeah, actually I can. I can get Haskell language server to highlight the type of this highlighted expression. So A to IOC, that is the type of the whole right-hand side of this first invocation of bind. And this function of type A to IOC picks up the A here. So then this part here, from here to here, is of type IOC. And that is again an invocation of bind, which as its first argument has this IO action, which is of type IOB, right? And then as its second argument has this function that goes from here until the very end and is of type B to IOC. And this then picks up the B, and then finally the invocation of return to FAB, that is of type IOC. That is something that I cannot highlight nicely, but I mean, so the type of this line is IOC. So it all matches up. Okay. So this was a little bit abstract perhaps, but it does serve to show that like what we've seen so far, we have been seeing quite a number of different functions already to combine I/O actions, but really they are all built in like fundamentally built only using two, return and bind. And the other special cases, they're still helpful because they can often apply to good purpose, like fmap and lift-A2. They're often useful and we can still use them, but they are not fundamental. Also the basic sequencing, it's not fundamental, very often useful, right? But at a ground level, we only need the abstract I/O type and this return and the bind operation. And then we have certain operations that also like they do real stuff, right? They are basically primitive I/O operations. We can think of getLine and putString as primitive I/O operations for now. So what we're going to do next is we're going to try to like write something like still small, but something slightly larger, right? Write some slightly larger programs using I/O and see how the patterns come back that we're used to, like things like recursion, right? And how functional programming as we know it goes together with this world of I/O actions that we now have available.